Welcome to you all. In this video, we have to learn the concept of UV visible absorption spectroscopic applications. In that previous sessions, we have to discuss the concept of UV visible spectroscopy, absorption spectroscopy, and the transition, energy level transition and all. This is continuations of this previous unit. In this unit, we have to learn the solvent effect on spectral lines, bathochromic effect or redshift, hypsochromic effect or blue shift, hyperchromic effect and hypochromic effect. The conjugated systems and transition energies. The Woodward physics rules for calculating the absorption maximum in Dine's molecule, homoannular Dine's molecule, heteroannular Dine's molecule, exocyclic conjugated double bonds, Woodward Fisher rules for calculating absorption maximum, alpha and beta, unsaturated carbonyl compounds, rules for calculating absorption maximum for derivatives of acyl benzenes, and summarize that unit. Here the solvent is one of the very important play role in UV spectra. The compound peak could be absorbed by the solvent peak. So most suitable solvent is one that does not itself get absorbed in the regions under investigation. A solvent should be transparent in a particular regions. A dilute solution of sample is always prepared for analysis. It is clear that polar solvents gives rise to broad bands. Non-polar solvents show more resolutions. Completely removing the solvent gives the best resolutions. This is due to the solvent-solute interactions. The solvent can interact with the solute in its ground state or excited state through intermolecular bonding. The polar solvents like water has the ability of hydrogen bonding with the solute if the solute has a hydrogen bonding component or simply through induced dipole-dipole interactions. The non-polar solvents can interact through polarizability. This is due to the solvent tendency to align its dipole moment with the dipole moment of the solute. Depending on the interactions, this can cause the ground state and the excited state of the solute to increase or decrease, thus changing the frequency of the absorbed radiation. Due to this, there are many different transition energies that become averaged together in the spectra. This causes peak broadening. The effect of peak broadening are most serves for polar solvents, less so for non-polar solvents, and absent when solute is in vapor phase. What is the effect of on spectral lines? One of the very important content. The most suitable solvent is one which does not itself absorb in the region under investigations. A solute solution of the sample is always prepared for the spectral analysis. The most commonly used solvent is 95% ethanol. Ethanol is the best solvent as it is cheap and is transparent down to 210 nanometer. The commercial ethanol should not be used as it contains benzene which absorbs strongly in the UV region. Some other solvents which are transparent above 210 nanometer are N-hexane, N-methyl alcohol, cyclohexane, acetonitrile, diether. Some solvents with their upper wavelength limit of absorptions are given in the table 1 mentioned. Here we consider the N-hexane and other hydrocarbons can be used as these are less polar and have least interactions with the molecules under investigation. For UV spectroscopy, ethanol, water and cyclohexane serve the purpose best. The position of the intensity of absorption maximum are shifted for a particular chromophore by changing the polarity of the solvent. By increasing the polarity of the solvent, compounds like dienes and conjugated hydrocarbons do not experience any appreciable shift. Thus, in general, the absorption maximum for the non-polar compound is the same in alcohol as well as in hexane molecule. The absorption maximum for the polar compound is usually shifted with change in polarity of the solvent. Alpha and beta unsaturated carbonyl compound show different shift. We consider N2 pi star transition. In that N2 pi star transitions here that is less intense. In such a case, the absorption band move to shorter wavelength by increasing the polarity of the solvent. The N2 pi star transition, the ground state is more polar as compared to the excited state. The hydrogen bonding with solvent molecules takes place to lesser extent with the carbonyl group in the excited state. For example, the absorption maximum of acetone is at 279 nanometer in hexane as compared to 264 nanometer in that water molecule. In that pi to pi star transition, it is more intense. In such a case, the absorption band moves to long wavelength by increasing the polarity of the solvent. The dipole interactions with the solvent molecules lower the energy of the excited state more than that of the ground state. Thus, the value of absorption maximum in ethanol will be greater than that of absorbed in hexane. In short, pi star orbitals are more stabilized by hydrogen bonding with polar solvents like water and alcohol. It is due to greater polarity of pi star orbital compared to pi orbital. Thus, small energy will be required for such a transition and absorption show a red shift. N2 sigma star transition are also very sensitive to hydrogen bonding. Alcohol as well as amines form hydrogen bonding with the solvent molecule. Such associations occurs due to the presence of non-bonding electrons on the heteroatom and thus transition requires greater energy. In general, if a group means carbonyl is more polar in ground state than the excited state, then increasing polarity of the solvent stabilizes the non-bonding electron in the ground state due to hydrogen bonding. Thus, absorption is shifted to lower wavelength. If the group is more polar in the excited state, then the absorption is shifted to longer wavelength with increase in polarity of the solvent, which helps in stabilizing the non-bonding electrons in the excited state. It has been found that increase in polarity of the solvent generally shift N2 pi star and N2 sigma star bonds to shorter wavelength and pi to pi star bonds to longer wavelength. This is what absorption shift with change in polarity of the solvent. In absorption and intensity of shift, the shift of absorption position and absorption intensity due to change presence or removal of chromophore, oxochrome under solvent is denoted by particular terminology is known as absorption spectroscopy. They are bathochromic effect or red shift. The shift of an absorption maximum to longer wavelength due to presence of an oxochrome or solvent effect is called what? Bathochromic shift or red shift. For example, benzene shows lambda maximum 256 nanometer and aniline shows lambda maximum 280 nanometer. Thus, there is a bathochromic shift of 24 nanometer in the lambda benzene due to the presence of oxochrome NH2. Similarly, bathochromic shift of N2 pi star band is observed in carbonyl compound on decreasing solvent polarity. Lambda maximum of acetone is at 264.5 nanometer. Water is shifted to here 279 in hexane molecule. In that hypsochromic effect or blue shift, here the shift of an absorption maximum shorter wavelength called hypsochromic means blue shift. This is caused by removal of conjugation or change in solvent polarity. For example, we consider aniline is what? 280 nanometer. Anilinium ion is 254 nanometer. Hypsochromic shift due to removal of N2 pi star conjugation of the lone pair of electrons of the nitrogen atom of aniline. Protonated aniline has no lone pair of electrons for conjugation with benzene ring. Similarly, the hypsochromic shift 10 to 20 nanometer of the bond of carbonyl going to solvent ethanol to hexane. In that hyperchromic effect, we consider effect leads to an increase in absorption position intensity. It's called Emax is called what? Hyperchromic effect. The introduction of oxochrome usually causes hyperchromic shift. For example, benzene shows B band at 256 nanometer with Emax 200, whereas anilinium shows B band at 280 nanometer with Emax 1430, and the increase the 1000 to 30 in the Emax of aniline compared to that of benzene. This is due hyperchromic effect of this oxochrome in H2 molecule. Finally, in that hypochromic effect which leads to decrease in absorption intensity Emax called hyperchromic effect. This is caused by introductions of group which distorts the chromophore. For example, biphenyl shows lambda max 252 nanometer with Emax 19,000, whereas 2,2-dimethyl biphenyl shows lambda max 270 nanometer, Emax 800. The decrease of 18,200 in the value of Emax of 2,2-dimethyl biphenyl due to hyperchromic effect of the methyl group, which distort the chromophore by forcing the ring out of coplanarity, resulting in the loss of conjugation. All the effect discussed, and to summarize in that figure 2, this is called what? Bathochromic effect. This is what? Hypochromic effect. This is what? Hyperchromic effect. This is hypnochromic effect. Okay, just we consider here it greater than wavelength, that is bathochromic, less than that wavelength, that is hyperchromic, and greater than that intensity, that is called what? Hypochromic, and hypnochromic, like that. The conjugated systems and transition energies. When two or more chromophoric groups are conjugated, the absorption maximum is shifted to a longer wavelength, and usually the greater intensity compared to the simple conjugated chromophore. This is because the conjugation reduces the energy gap between electronic transitions level, that is, conjugation lowers the energy required for electronic transition. We know that as the energy of electronic transition decreases, usually their probability increases, and so Emax also increases. Next we are discussing that Woodward-Fisher's rules for calculating absorption maximum in dienes molecule. This is also one of the very important. We consider this table is one of the important. According to these rules, each type of dienes has certain fixed basic value and the value of absorption maximum depends upon. Here, the number of alkyl substituents or ring residues on the double bond, the number of double bond with extended conjugations, and presence of polar groups such as Cl, Br, OR, and SR. The ring residue is a carbon-carbon bond, not a part of the conjugated system but attached to any one of the carbon atoms of the conjugated polyene system. The various rules for calculating the absorption maximum in case of dienes and trienes are summarized here. The parent value for butadiene system and or acyclic conjugated dienes here 217, acyclic trienes 245, homoannular conjugated dienes is 253. Heteroannular conjugated dienes is 15 nanometer. The increment of each substituent, alkyl substituent is there, that is 5 nanometer. Exocyclic double bond is 5 nanometer. And double bond extended conjugation is 30 nanometer. We consider oxochrome, here OR plus 6 nanometer, SR plus 30 nanometer, Cl or Br that is 5 nanometer, NR2 60 nanometer. Now we consider that homoannular dienes molecule. Homoannular dienes molecule. In that ಒಂದು ರಿಂಗಲ್ಲಿ ಎರಡು ಡೈನ್ಸ್ ಇದೆ ಅಂದ್ರೆ that is called what? Homoannulars ಅಂತ ನಾವು ಹೇಳ್ತೀವಿ. This is also a homoannular dienes molecule. In homoannular dienes, conjugated double bonds are present in the same ring and having a cis configuration. The cis configuration causes strains which rises the ground state energy level of the molecule, leaving the high energy excited state relatively unchanged. Okay. Consider that acyclic dienes exist mostly in the stainless strands configurations which strainless with relatively lower ground state energy levels. Thus their absorption appears at shorter wavelength. Hence 1,3 cyclohexadiene shows lambda max 256 nanometer, whereas 1,3 butadiene shows lambda max 217 nanometer. As due to the shorter distance between the two ends of chromophore, cis dienes gives lower A max than that of the trans diene. This is what homoannular. So 256 nanometer. This is what open chain. That's why that is what here 217 nanometer. In that heteroannular dienes molecule, this is called what? Heteroannular dienes molecule means conjugated bonds are not in that same ring and these have trans configurations. That is what heteroannular dienes molecule. That lambda max for that heteroannular dienes molecule is here 256 nanometer. In exocyclic conjugated double bonds, this is exocyclic conjugated double bond here, this is endocyclic, this is exocyclic, this is one exocyclic double bond here. These are two exocyclic double bonds. Exocyclic ring B, this is an endocyclic ring, that is what? A, like that. 3 exocyclic double bond here, 1, 2, 3. 3 exocyclic double bond. Here, note that the same double bond may be exocyclic to one ring while endocyclic to the other, and sometimes the same double bond may be exocyclic to two rings simultaneously. In alkyl substituents and ring residue. Only the alkyl substituents and ring residues are attached to the carbon atom constituting the conjugated systems of the compounds are taken into account. The following examples indicating such carbon atoms by numbers and alkyl substituents and rings residues are dotted lines. The two alkyl substituents are mentioned here. 2 ring substituent. Here the 3 ring substituents. These 2 alkyl substituents and 3 ring substituent. This 1 alkyl substituents and 3 ring substituents. Next we consider how to calculate that. In a compound containing both homoannular and heteroannular diene system, the calculations are based on the longer wavelength, that is homoannular diene system. The calculated and observed values of lambda max usually match within plus or minus 5 nanometer. The following examples are illustrated. Calculate the absorption maximum in the UV spectrum of 2,4 hexadiene. The basic unit in 2,4 hexadiene is a butadiene. There are 2 alkyl substituents on its here. This one. What is the base value for this? This homoannular. That's why what is this? 270 nanometer. There are 2 alkyl substituents are there. Except this here 1, 2. 2 alkyl substituents, 2 into 5, 10 nanometer. What is the total value? 227 nanometer. The absorption maximum in the UV spectrum of this one. Here how it is. Says the thing here. It is a butadiene system. There are 2 alkyl substituents are there. 1, 2 alkyl substituents and 2 ring residues. These ring residues on the double bond. Moreover on and 1 exocyclic double bond. What is that basic value here? 217. 2 alkyl substituents 10. 2 ring residues here 5 into 2. That is what? 10. 1 exocyclic double bond. That is what? 5. Totally 242 nanometer. This is also there. This is the heteroannular dienes. The base value is 215. The 4 ring residues are there here 4 into 5. What we are getting 20 nanometer to 35 nanometer. This is the calculate the absorption maximum for that in molecule. Here, what is the base value for this? This homoannular dienes molecule base value is 253 and 3 ring residues are there 15 and 1 exocyclic double bond totally 273. What is the observed value here? 273. This one is also we consider here the base value for this. Here 253, 2 extended double bond conjugated system 60 nanometer, 5 ring residues 25, 1 exocyclic double bond 5 nanometer, totally 343 nanometer. Is the what? UV visible value for that. Lambda maximum value. The Woodward-Fizzer rules for calculating absorption maximum alpha beta unsaturated carbonyl compound. Here we consider alpha beta unsaturated ketone is taken as 215 nanometer. The alpha beta unsaturated ketone may be cyclic or 6 member. For a compound CHCOX, the basic value is 250 nanometer, where X is what alkyl group, X is equal to H. The basic value becomes 207 nanometer. The basic value is 193 nanometer if X is OH or R. This is also similar to that here for each exocyclic double bond 5 nanometer. For each double bond endocyclic in 5 or 7 membered, ring except cyclopentane is known the 5 nanometer. For each alkyl substituent or ring residue of alpha position, that is 10 nanometer, beta position here 12 nanometer, gamma or delta higher positions we consider 18. For each double bond extended conjugation is 30 nanometer. For a homonuclear or homoannular conjugated ions 39 nanometer. These are all for chromophore. The increment of nanometer for positions with respect to the carbonyl group. If I consider these data, we have to calculate. This is what calculate the ethanol for the given structures. Here what? Alpha and beta. Okay. What is this value here? 215. And 2 beta alkyl substituent. This is what? Alpha, beta. 2 beta alkyl substituent is there here. 12 into 2, 24. Totally is what? 239 nanometer. The next lambda maximum for these structures. What is the basic value for this? This is carbon, this is alpha, beta, we consider 215. And the 2 beta ring residue. 2 beta ring residue, 24. 1 exocyclic double bond is there, that is called what? 5 nanometer, totally 244 nanometer. Observed value is 241. That is practical. That calculated value for this is alpha beta unsaturated cyclopentanone system. Basic value is 202. 1 beta alkyl substitutions here 12 nanometer. 1 exocyclic double bond 5 nanometer. 1 double bond extending conjugation is 30 nanometer. 1 gamma ring residue is 18. 1 delta residue is 18. Totally 285 nanometer. The observed value was found to be 287 nanometer. The calculate the lambda maximum for these given structures. Here also we consider this homoannular and this is alpha and beta. We consider here base value is 215. Alpha ring residue is 10, beta ring residue is 10. 1 exocyclic double bond is 5. Homoannular conjugated ion is 39. 1 double bond extended conjugation is 30. Totally 317. Maximum what examples we are mentioned here, those examples are asking in that examinations. Please be careful, you have to study it in that applications level. What is the rules for calculating absorption maximum for derivatives of acyl benzenes? Like Woodward-Fisher rules, Scott devised a set of rules for calculating the absorption maximum for the derivatives of acyl benzenes. These rules helps in estimating the position of absorption maximum in ethanol in a number of monosubstituted aromatic ketones, aldehydes, acids and esters. What are those examples? The basic value is 246 nanometer if X is an alkyl group or polycyclic residue. If X is hydrogen atom, the basic value becomes 250 nanometer. The basic value is 230 nanometer if X is OH or OR. The structural increments in nanometer for further substitutions on the aromatic ring in the ortho, meta and para positions are in that given table. This is what alkyl group, this is ortho position, meta position and para position. This is the increment in nanometer positions of substituent. This OH, ClBr, NH2, NHC, NR2 molecule with respect to the positions increment in that positions mentioned. Here also to calculate the absorption maximum in ethanol for para-chloroacetophenones molecule. Here the basic value is what? Here ketone acetone group is there, that is 246. 1 chloro substituent is there, that is 10 nanometer, totally 256. Next we consider here 246 and OH substitutions in that meta position, that is 7 nanometer. OH substitutions in that para positions, this is meta, this is para position, that is what 25 nanometer, totally 278 nanometer. that absorbed value is 281 nanometer. That absorption maximum in ethanol for the following compound, this one, the basic value is 230 nanometer. The basic value, you go through that rules, okay, and beta position and Br position that is present in that para position, that value is 50, totally 245 nanometer. Like that, you have to study some important sums based on that electronic transition spectroscopy. A good solvent should not absorb UV radiation in same region as the substance whose spectrum is being determined. Usually, solvent which do not contain conjugated systems are most suitable for this purpose. Although they vary as to the shortest wavelength in which they remain transparent to ultraviolet radiation. The solvents most commonly used are water, 90%, ethanol and hexane. There are several types of electronic transition available to molecule, including sigma 2 sigma star, pi 2 pi star and n 2 pi star. The solvent used in absorption spectra has an ability to influence the wavelength of UV light which will be absorbed by molecule. The transition of n 2 pi star type are shifted to shorter wavelength by polar solvent. In some cases, the excited state may form stronger hydrogen bond with solvents than corresponds ground state. In such cases, a polar solvent would shift absorptions to longer wavelength since the energy of the electronic transition would be decreased. The transition of the type pi to pi star are shifted to longer wavelength by polar solvents. And with the lambda maximum values of conjugated systems often requires difficult calculations using molecular orbitals theory. They can readily be estimated using a set of empirical rules depending on whether the basic chromophore is conjugated dienes or an alpha beta unsaturated carbonyl compounds or benzoyl derivative. For example, 1,3-butadiene, the S trans conferred is rather more stable than the S6 conformations. But for other substituted dienes, the reverse is usually the base. Because of steric hindrance between the substituents. In general, the extent of p orbital interactions is rather greater in S6 conform than the corresponding S trans conform, leading to higher lambda max values for the former as indicated in diagram below. That Woodward-Fisher rules break down when applied to molecules that have some kind of strain around the chromophore. They also pour predictions of lambda max for cross conjugated molecules. The extended other than the end of the chromophore. The most cases resonance impeded due to distortions caused by strain. So Woodward-Fisher rules predict the lambda maximum that are too high. From these very important questions are mentioned here, explaining the following effect of increasing solvent transition polar probability, bathochromic and hypsochromic effect, hyperchromic and hypochromic effect. Describe the Woodward-Fisher rules calculating the absorption maximum in dienes, ethylene, naphthalene, anthracene, butadiene. Explain why these molecules and how you will distinguish between following pairs of compounds by UV spectroscopy. Which of the following do not absorb the UV regions? And explain why methyl iodide has both lambda maximum and E maximum higher than methyl chloride. And no N2 sigma star transition is absorbed by protonated triethylene. These are all very important. These are all important questions generally asking in that examination, in that applications level. Okay, please go through that. Read well. Thank you. Thank you one and all.